Okay, I'd like to give you some applications of Ampere's law. So this is applications of Ampere's law part 1. Let's say we have a circular cross section of wire. Let's say the wire's coming like this out of the paper and into the paper. And let's make some dots here to show this is current. The current is actually coming out like this. And let's say it's uniformly distributed. So in fact, let's talk about the amount of current coming out. We'll talk about it in terms of current density. So current density is a known. We'll call it J. Remember, J is equal to I over A. And that's a known. I'm going to have J in my answer. And what I'm going to want to find is the magnetic field, say, in here a distance r away. Lowercase r away. And eventually I'm going to also want to know what the field is out here, another distance little r away, we'll say. But let me first find the magnetic field a distance r away, like say right there. And we also have to make one other assumption, and that is that that mu naught is equal to the mu of this material. So this material has its own permeability, and let's say that it's pretty much equal to the permeability of free space. Okay, so if I want to know the magnetic field there, I'm going to draw an Amperian loop, and this Amperian loop is going to be circular. So there it is, a distance r away. And so all that matters is the current that is passing through the Amperian membrane. Here's the Amperian membrane. Okay, so I'm going to write down Ampere's law. Mu naught times I through the Amperian loop is equal to the integral, the closed loop integral, the closed path integral, closed loop or closed path integral of B dot dl. And just to remind you, this B is not just any old B, it's the B on the Amperian loop. It's the B right here. And these DLs, these are the DLs that make up the Amperian loop. These are little line segments, DLs. Okay. So as you might guess, the B right here is going to be, well, let's just talk for a moment about the B that's due to these guys out here. We're going to get a cancellation effect from these because the B's from here are right there. They're going to be putting a field that way, where the B's from here are going to be putting a field this way. And so you're going to get a cancellation effect there. And I'll talk more about why that is a cancellation effect in a later video, but for right now, the only B that's going to matter, according to Ampere's law, is going to be the B that's enclosed, or the I that's enclosed. All the rest of it cancels, kind of like in Gauss's law, where we said the same thing. And so I'm going to say that starting here, mu naught. Of course, if it's not mu naught, I might have to use whatever the mu is, but I'm going to just call it mu naught for right now because it's equal. The mu in there is equal to mu naught, and then the I through the Amperian loop. So the I is going to be just J times the area, this area. So it's going to be J times this area. So pi times little r squared. You see how that gives me the I through the Amperian loop? That's equal to B dot dl. So now the first thing I'm going to do is I'm going to get rid of the dot product, because you see the B right here, if I use my right hand, it's circulating that way. So the B right here is going this way. That's a B, a B, that's a B, a B. That's the magnetic field direction, magnetic field direction. But the DLs are also going that way. Just draw a bunch of little DLs. Now, how many DLs are there around here? An infinite amount. Why? Because they're infinitesimally small, each one. But the B and the DL are in the same direction. So we just lost the dot product, because what is the dot product doing? It's taking the part of B that's that's in the direction of dl and then multiplying it by dl. So how much of B is in the direction of dl each time? Answer, all of it. So, and it does give you a scalar product, so that's why the dot product disappears there. And so that's because the argument for this last step is because B is parallel to dl at each point on the Amperian loop. Okay, then I'm going to argue that you can pull the B out of the integral because of the symmetry of the situation. Why would B be any stronger here than here than here than here? It's so symmetrical that it wouldn't. And so mu naught times j pi r squared is equal to, when I pull that out, it's just going to be the sum of all the dl's around the loop. And so the sum of all the dl's around the loop are gonna, when you add them all up, you're just gonna get 2 pi r. Okay, let's get rid of the pi, get rid of one of the r's, and bring the 2 on the other side, and apparently B is equal to mu naught times j times r over 2. Okay, so if I were going to plot that, see what that looked like on a graph, apparently if I go out twice as far from the center, these are all constants, I get twice the B. If I go out 3 times as far, I get 3 times the B, all the way out to the edge there. So I'm only going to plot this from 0 to r for right now, because I don't know about outside. But inside, it's linear proportion. B is directly proportional to r. Okay, so that's for inside. Now, I will give you the argument for outside in the next video. All right, thanks, bye.